Alright guys, again this video will only be for my personal documentation purposes. In this video we will try to plot the shear stress profile in a pipe, and just like our previous video, the geometry of the pipe shall be 3 meters in length. The Reynolds number will be 2100, and the flow will be considered laminar. It is a laminar flow. The length of pipe is 3 meters and the diameter will be 2 centimeters. Again, in order to get this profile, we will be using the basic equation, which we find it in every fluid mechanics textbook, which will be mu times change in velocity with change in y. I could say mu times change in velocity with radial direction. In our case it will be this, because our radius will be in the y direction. Also, a point to be noted is we will not be modeling for a complete circular cross section of the pipe in order to reduce the simulation time. So we will actually just consider a section of a cross section. The angle we will consider will be 45 degrees, and if you actually look at the pipe, this is the pipe length in the x direction, this is our radial direction distance in y direction, and our z direction will not have anything except the cells. We will divide it into 3 cells in the z direction, and this face we are going to take it as symmetry boundary condition. And alright, I guess this is enough. So we shall try to plot for the shear stress. In the previous video we have plotted already for the velocity profile successfully. So let's have a look at the shear stress profile. Okay, so the application, the OpenFOAM application that we shall be using will be an OpenFOAM solver, the description for which you could find it, let's say here. Sorry. If you open the C++ file, you see that this is a transient solver for incompressible laminar flow of Newtonian fluid. So the fluid that we have considered is water, which is of course Newtonian in nature, and the flow is laminar because the Reynolds number is 2100 and it's an incompressible flow. So the application is OpenFOAM. We see that it applies this algorithm applies a Peso algorithm, which you could find in any literature. And of course, in order to understand the complete algorithm in C++, we will have to understand the language, which at this point of time I'm afraid I don't know much about. So we could actually go back to my program, and if you see here, I've already run the program, and I have 50 time steps here, which can be checked from this. If you have a look at this, we see the total time is 20 seconds with a time step of 0.05 seconds, which makes the total number of time steps will be exactly this, 20 or 0.05 is 400. We're gonna write the time at every 8th time step, which makes it, we will have 50 time steps in all. So that is one case. So we could actually go back, and I could run OpenFOAM, but that would just be redundant. Since I've already run OpenFOAM, I could just go directly to post-processing and start with the shear stress plotting. So in order to start with our shear stress plotting, we can do one thing is we can run the application first. We'll have to run the application. Always go for surface with edges. Alright, if you have a look here, let's have the actual sheet view, in which let's have a look at the velocity. The velocity we see is in vector form. This is the u component, the v and w component. Of course, the v and w component will be 0, as our velocity given is only in the u direction and it is laminar in nature, so we will not have the v and w component of velocity. But we can actually first calculate the magnitude of this in order to convert it into scalar. So let's do that. You could just say, you could give this name anything. For example, I just give this magnitude of u. I can have this as magnitude of u, and I'm gonna hit apply. So here we go, we have magnitude of u, which is now a scalar. You can also rename this, which is actually habit. And once we do that, we can go for calculation of gradient. As you see here, now we need a gradient of u in the y direction. In this case, gradient of u in the y direction will be the most prominent, so we don't have to worry about that in a specific direction. So let's go for gradient of u, which can just be like CTRL space, or you could just say in filters, you could go to alphabetic and you'll have it somewhere here. Gradient of unstructured data set. Here we say this is grad of mag u. I'm gonna hit apply. This gives us the gradient. So now we need what? We have the gradient. We know this is a constant. We're just gonna put in the value of constant. The value of mu that we take in this case is 0.001002 Newton second per meter square. I think this is true. Is that the case, or is it Pascal second per? I think it's Newton second per meter square. Okay, so this is the value of mu, which will be multiplied by the gradient that we already have. So let's have that. We're gonna do again a calculation, which is actually this will be our tau finally. 0.00102 times the gradient of mag u. Gonna hit apply. This is our shear stress, right? Now you see the shear stress is again in a vector form, shear stress in x, y, and z direction. So what we will do is we'll just calculate the magnitude of shear stress. You don't really have to, but I'd like to do that. Magnitude of shear stress, of course shear stress is tau, so we could just say mag of tau. You can give this name anything, but here you'll just have to use magnitude of our tau. Now that becomes a scalar, so we'll just remove tau. Okay, what else do we not need? Okay, we don't need grad. We have velocity, we have shear stress, and magnitude of u. Alright, you can remove this for now. And now, if we do plot, then what really happens is the plotting will be done on the xy plane. You see, this is the xy plane. So the plotting is going to be done in the xy plane. So that is going to just give us just this distance. We need it for the complete profile. We need it for the complete diametrical distance. So what we can do is we could actually use some tools in post-processing to get to that, and that is in alphabetical you can use the reflect, and you can ask the tool, the post-processing, so you can just reflect it along the y direction. Okay, it's not about the axis, it's along the axis is what they ask. So you reflect it along the y-axis, you're gonna hit apply. You have this. Now you can just do the plotting. Remember, this needs to be highlighted. You plot over line. You can just say y-axis. Now, as I said, my 2.1 meter is in the fully developed region. 2.1 meter from the inlet is fully developed flow. So I'm going to change these things. I'm not going to change these things. I'll just be changing this. I'll hit apply. I'll just probably reduce this size to 50, so that if I do extract it, then it gets easier for me. Alright, so now I don't need all of these things. I just need my shear stress, magnitude of shear stress. I can also take this. Oh, I'm sorry. What is this? Oh, that's magnitude of magnitude of shear stress is what I need. Okay, so that's about it, right? But there's something not right with this. Well, we see in literature, we again see that the shear stress is in the x direction, and this is our y direction, is our radial direction, so we'll just have to invert it. The x direction will be our shear stress, and our y direction will actually be this, but that is going to give a wrong legend. We can actually change that here. You can just say this is our shear stress. We'll make it fancy by actually giving it a name. Let's say shear stress profile at 2.1 meters from inlet. That's about it. You could also give it, this is of course your radial direction, try distance, and this is your shear stress. There you go. So this is almost identical to this. Well, there are some changes. We could actually work on this. Probably one of the things that we could do is if we have finer mesh near the axis, then we could take care of these lines. I'm not very sure about that, whether we could or not. I'll let you know maybe in the future videos. Okay, if we have a spreadsheet view, which we can have, okay, I'm going to remove all these things, the arc length, the gradient, the pressure file can be there, even the shear stress. So we have like I said, we just did it for 50 points. So at this particular point, 2.1 in x direction, so we can have the magnitude of shear stress, the magnitude of velocity, as well as the pressure. You don't really need the pressure, because we need the pressure drop across the length of the pipe and not at a particular location. So you can remove that. Maybe you could just extract this. You can just export this, so anywhere you need. And remember, this will be in a .csv format, which is actually a comma separated file. This is basically a text file that allows data to be saved in a structured format. This is different than our .xlsx file, but yeah, it does open in Excel. So you could actually extract this data, import it, and open this in MATLAB and do an analysis on this with the analytical Hagen-Poiseuille equations. I myself have done that. Maybe I'll show it in the next video or so. Alright guys, thank you. That's about it.